three common household items represent three kinds of chemical compounds with which you will be continually concerned in your study of chemistry: acids, bases, and salts. Vinegar is an acid. Household ammonia is a base. Table salt, sodium chloride, is one of a large number of compounds called salts. What are acids, bases, and salts? What are the relationships between them, and why do they react as they do? In answering these questions, we will discuss briefly three of the theories that scientists have spent years in developing. The classical theory of acids, bases, and salts, which we still use in expanded form today, was proposed by Svante Arrhenius in 1887. Arrhenius knew that pure water was a poor conductor of electricity. Yet when certain substances were dissolved in water, these liquid solutions would conduct an electric current. Why? Arrhenius proposed this explanation. When molecules of certain substances dissolve in solution, they dissociate or separate into smaller charged particles or ions, which carry the current. According to Arrhenius's theory, a molecule in solution would dissociate into positive and negative ions, which would be attracted to oppositely charged poles. Another diagram will illustrate what would happen when the current is turned on. Positive ions near the positive electrode will be slightly repelled from it. Negative ions will be attracted to it and will give up their electrons. At the same time, negative ions are being repelled from the negative electrode, and positive ions are being attracted to it. The Arrhenius theory offered one explanation for the behavior of electrolytes: acids, bases, and salts. In the classical Arrhenius definition, a substance such as sodium hydroxide, which dissociates in water to yield OH, or hydroxyl ions, is a base. A substance such as hydrogen chloride, that dissociates in water to yield hydrogen ions, is an acid. Arrhenius believed that the hydrogen ion could exist free in solution. Later work indicated that this ion exists in water solution only as a hydrated hydrogen ion, the hydronium ion. The hydronium ion is a water molecule with attached proton. It is a hydrated proton. The hydrogen ion, or proton, is often written this way. The hydronium ion also explained why hydrogen chloride doesn't conduct electricity until it is dissolved in water, and the dissociated hydronium ion and the chloride ion form. This concept helps explain the reaction between ammonium hydroxide and hydrochloric acid, which we can express like this. We say the reaction goes to completion because a very slightly dissociated substance, water, is formed. This is an example of the expanded Arrhenius theory, which is still taught to introduce students to acid-base reactions. In 1923, Bronsted and Lowry organized and enlarged the newer concepts, using a definition based on the hydrogen ion, or proton. They defined an acid as a substance which dissociates to furnish protons, a proton donor. A base, then, becomes a substance which accepts protons, a proton acceptor. In this concept, ammonia gas can be considered a base, as it will accept a proton to become an ammonium ion. The electronic structure of ammonia gas shows an unshared pair of electrons. In 1923, physical evidence led an American chemist, Gilbert N. Lewis, to believe that a proton from an acid readily becomes attached to this unshared pair of electrons in some other molecule. An acid, then, becomes a substance which accepts an unshared pair of electrons. Both the Lewis and the Bronsted-Lowry theories explain acid-base reactions in systems other than the aqueous solution system of Arrhenius. Of the three theories we've seen explaining acid-base reactions, we'll use the Arrhenius classical theory, remembering that others do exist. How can we tell that a solution we have is an acid? The liquids in these beakers all appear to be identical, colorless, water clear. Yet one is an acid, the others are not. Long ago, chemists discovered that certain substances, which we call indicators, show color changes when treated with an acid. Litmus paper and methyl red are common indicators. First, we'll test these liquids with blue litmus paper.